Okay, because we've got a limited time today, I'm going to get started. I realize that there'll be some individuals that are joining in after we've officially got started, but I don't want to, I want to use as much time as I can today. So, first of all, my name is Shawn Bontaine. I'm with Javelin Technologies, and it is my pleasure to be with you today to talk to you a little bit about geometric dimensioning and tolerancing. So I was asked to put on just kind of a little exposure to GD&T, just to kind of give you a little bit of a taste and get you thinking about geometric dimensioning and tolerancing. So one of the things that I'm going to do is I'm just going to minimize actually, I'm going to go ahead and turn off my camera just to make sure that I'm not blocking any of the screen that you're seeing. Today, what I'd like to do with you is I'd like to talk to you a little bit about the benefits of geometric dimensioning and tolerancing and why we take the time to apply GD&T to our drawing packages. I also want to give you kind of a sample material from the actual course. Javelin runs two geometric dimensioning and tolerancing courses. We have a fundamentals course, which is a 12-hour course, and we also have an advanced course, which is also a 12-hour course. So what I'm going to do is I'm going to pull out a little bit of information from the first course, the fundamentals course, just to go ahead and kind of give you a feel for what we cover in the course itself. Just want to make sure that everybody can hear me okay and see my screen. At, okay. And Paige is on with us as well. She'll be manning the chat and um, looking after any kind of issues. Okay, so looking good. Excellent. Okay. So as I mentioned, we want to give a sample of the material from the course content. And then near the end, I'll give a summary of the actual full course outline, just so that you've got a good feel for what we cover in that 12 hours. And then I also want to allow some time for questions if time permits. So just to continue on, we're using the Zoom interface for this webinar. So with the actual Zoom interface, just keep in mind right at the bottom of your screen, there is a mute and there is a share camera. So you could see the kind of interface. Let's just talk about those. The actual mute right now, everybody's muted just so that there's no interruptions from background noises, etc. But later on, when we get to the answering questions, feel free to unmute and ask questions. You also can refine your audio settings if you finding that you're having difficulty hearing. There's also the chat. There is a chat button that you can then throw into the chat. And I might not be paying too much attention immediately to the chat, but I'll definitely during questions go back and look at the chat to make sure that I try and answer questions that have come up. And there's also some nonverbal as well, where you can communicate as well. So just a little bit quick background on myself. I've been with Javelin for about 10 years now. Excellent company and really enjoy working with Javelin and for Javelin. My work experience is before coming to Javelin, I've worked at companies like ATS, Automation Tooling Systems. I've been a business manager with the technical training group. I've worked in industry as a tool designer, designing jigs, fixtures, gauging. My background is basically mechanical engineering. I have my qualification in geometric dimensioning and tolerancing, and I've had that qualification for about 20 years. And I've been teaching in different companies for pretty much that 20 years as well. So just a little bit of a background on why I teach the actual geometric dimensioning and tolerancing. So I want to start off by just asking a couple of questions. I want to get you thinking about what is drafting. So when we think about what drafting is, so maybe in the chat, if I just kind of turn my chat on, if somebody would like to go ahead and just answer their thought on what is drafting, or unmute for a second and just volunteer your thought of what is drafting. Okay, quiet group today. Okay, so let me answer that one. Drafting is a form of communication. When we go ahead right now, I'm communicating to you verbally. You can hear me speaking and I'm doing verbal communication. Drafting is communicating through the form of a drawing. So taking ideas and information and communicating through an actual drawing and drawing packages. It's really important to understand that it is a natural form of communication. The other thing that I want you to start to think about is what is important to a drawing. Things that are important to drawings are the fact that they're complete. There's nothing worse than getting a drawing package on the shop floor and half the information is missing. Another thing that's important to a drawing is that it's clear and concise because, again, it is a form of communication. So it is important that it's clear and easily understood. Also, accuracy. Again, as we apply tolerances to our different features, we want to make sure that we get interchangeability and that we're making things to the appropriate tolerances so that we do get that interchangeability. And the other thing that's very important to a drawing is standardization. We want to make sure that, again, if I'm looking at a drawing package here in my office, somebody on the shop floor is looking at that drawing package, or someone somewhere across the ocean is looking at it, we're all going to interpret it the same way. So it needs to be clear and concise. It needs to be accurate. It needs to be complete, and it needs to be standardized. The other thing to keep in mind is keeping in mind that drafting is a form of communication. Geometric dimensioning and tolerancing is concerned with form, fit, and function. So there's a number of different benefits of taking the time to apply GD&T to your drawing packages. Number one, GD&T ensures that the functional requirements of the assembly are transferred down to the individual parts, therefore satisfying that form, fit, and function. It also tends to reduce scrap and rework because now someone looking at the print has a true picture of what is required, the actual true design intent. And we also get better and more consistent results at the time of assembly and with insertion of spare parts. GD&T also creates a different thought process during the design stage of the parts. Designers now relate and dimension based on the relationship of mating parts, focusing on the function of the assembly and eliminating assumptions on the shop floor. And that's a very important thing because it is a form of communication. Always remember that when you produce a drawing, you're very intimate with the drawing, you understand it, you were the one that produced it. When somebody's reading a drawing, and especially with globalization and outsourcing, somebody might be taking a look at this drawing that has no idea where this part goes. The only information they have is from the actual drawing itself. So it's really important to communicate effectively that not only the actual features and the tolerances, but also the form, fit, and function. That way somebody has a clear and concise understanding of what needs to be done for that part, whether they're making the part or inspecting the part. And another benefit of geometric dimensioning and tolerancing is it utilizes universal symbols such as flatness, perpendicularity, and it places it on the drawing to reduce writing on the drawings. Now, one thing that we're going to talk about right near the beginning here is the whole concept of datums. By definition, datums are theoretical exact points, axes, and planes. These elements exist within a framework of three mutually perpendicular intersecting planes known as the datum reference frame. The purpose of the datum reference frame is to immobilize the part, taking away the 6 degrees of freedom, the 3 translational and 3 rotational, and establishing the actual origins. Datums can be applied to surfaces and to features of size. When we take a look at the actual datums themselves, they're identified through a datum identifying letter. So the letters of the alphabet, A, B, C, D, etc. There are 3 that are avoided in GD&T, but other than that, the rest of the actual alphabet is good. At, the other thing to keep in mind, as I mentioned, that we can apply datums to surfaces. What the Everything in the actual standard, and the standard is the ASME Y14.5 2018 standard. That is the latest and greatest standard. It refers to everything as a feature. It then deviates and says that there are datum features without size, which are surfaces, and these datums are commonly applied to surfaces, and they become the locations for positioning features and locating from derived dimensions. Datum features of size. When we apply datums to features of size, right? Datums can also be applied to those features of size. The features generally selected on the basis of its geometric relationship to the toleranced feature. Note the datum is applied on the feature, not the feature's axis. It implies the feature's axis. So again, you can see on the screen different ways of calling up the actual physical feature of size. In illustration A, we're calling up the actual small diameter as datum P. It's then implying the actual axis created from that feature as the actual datum. When we go back to actual surfaces, notice here there's four main ways of applying datums to surfaces. And here's a number of examples of applying it to a feature of size. Now, when it comes to feature control frames, with feature control frames, think of feature control frames as a series of segments or compartments that stack together to communicate information. So a feature control frame placed on a drawing, it's the order that's important. The initial first compartment or segment that makes up a feature control frame, as you can see in figure 6-24, is the actual geometric characteristic symbol. And we're going to be talking a bit about those characteristic symbols today as well. So the second compartment is the actual tolerance. So in this first example here, we have a flatness requirement of 0.08. In the second example, we have a straightness requirement of 0.14. Now, when we take a look at this in the actual tolerance portion, you can come across other symbols. The most common symbols are like a diameter symbol, in this case, which indicates that we're talking about the straightness of an axis. It is a feature of size like a shaft, and we're talking about the straightness being applied to the axis of the shaft. You can also come across material condition symbols as well, and we'll touch on that a bit today as well. If we take a look at figure 6-25, now all of a sudden we notice that we have another feature control frame here, but it actually has a datum reference. These previous two had no datum reference, just the characteristic symbol and the tolerance. That is because both of those are form tolerances, and form tolerances are not related to datums. But if we take a look at the figure 6-25, we see that we have a perpendicularity of 0.05 to datum C. In other words, we have a 90-degree relationship as a condition to datum C. In the actual tolerance portion here, we see that it is a diameter. So that's telling us that it is something like a hole or a boss that's sticking up, and we're talking about the perpendicularity of the axis. The datum reference is just saying what this 90 degrees or perpendicularity is related to. And in the feature control frame, we can see how much we can vary from that and still be an acceptable part. So feature control frames are just a way of communicating your design intent on a drawing. It always starts off with the characteristic symbol, followed by the allowable tolerance or permissible tolerance, followed by any datum references as applicable. When we talk a little more about datum references and feature control frames, just keep in mind that the order of the actual datums being called out in a feature control frame, it's not the letter that establishes primary, secondary, or tertiary. It is the order that they appear in the feature control frame. So in this case here, in the top one, we have primary datum, A, the first one that's after the actual allowable tolerance. Then we have the secondary datum, followed by the tertiary datum, ABC or HDG. As we get into the physical course, we talk about functional datum selection, and we talk about looking at the assembly and how the parts go together in order to understand where your primary, secondary, and tertiary datum would be drawn from. But for now, just mentioning that in a feature control frame, the first one after the tolerance is always the primary, the second one is the secondary, and the third one is the tertiary. And you don't need always 3 datums. Sometimes, depending on the actual application, you need 1, 2, or 3. Another thing to keep in mind with feature control frames is how they're placed on drawings. There's an example that you're seeing right now on your screen, and that example shows the 4 most common ways of placing feature control frames or coming across feature control frames on a drawing. The most common method is to attach it right to the feature related callout. So in other words, we're calling out 8 clearance holes here on that flange. And not only do we have to meet the actual physical size requirement of those features, but it has a positional requirement of so much to A and C. So the feature control frame is attached right to the actual callout, and it moves with it as it gets moved on the drawing. Another example would be over here in the middle where we've got an actual M42 thread called out, and there's a positional requirement attached to it. The second method of coming across a feature control frame on a drawing is by means of attaching a leader pointing to the actual surface or to the physical feature of size. In this case here, we see the large flat surface at the back here has a flatness requirement of 0.02 to qualify or establish this surface as our datum A. Here we have our inside diameter here. Not only does it have a physical size requirement, but it has a circular runout requirement to A and B in order to qualify or establish it as datum C. So that is the second way that you can come across by attaching a physical leader pointing to the feature of size or to the surface. The third method of applying a feature control frame or coming across a feature control frame is to take a surface where it appears as a line and to bring an extension line up and attach it right to the physical surface. So here we're saying that we're applying these callouts here to this physical surface, and we're doing it by means of an extension of the surface. There was a gentleman or a person that raised their hand. I'll take one quick question and then I'll reserve the questions to the end.
Hello?
Yes.
Hi, thank you so much for this the webinar. I really appreciate that.
My pleasure.
Yeah, why I do not see A, B, and C datum planes usually is supposed to be like physically supposed to be the stated on the surface, correct? So I see the datum plane under this tolerance, the flatness 0.02, but physically it's supposed to be shown there, no?
Okay, so one of the things in the course itself, we get into talking about qualifying datums versus designated datums. And in this case here, this is what we call a qualifying datum, where if it meets this physical flatness, it then qualifies and establishes as datum A. Designated datums are where you just apply the datum to either a surface or a feature of size, and it just designates it as the datum. So in the course itself, we also get into talking about how many datums are required, and we'll talk about how datum reference frames work inside of drawing packages. And we talk about assigning datums and the thought pattern behind the datums and how many datums you need. So I don't know if I answered your question 100%
Yes.
there.
Okay, I got
Okay.
it.
Yeah. No, excellent.
Thank you. Thank you, sir.
Okay, no, you're welcome.
Thank you, Shawn.
The next thing, oh, I apologize. I went over the first couple methods. So attaching it to the actual feature related callout, using a leader that points to either a surface or a feature of size, bringing an extension line up from a surface where it appears as an edge. And the fourth common way of applying a feature control frame is attaching it to the actual physical feature size and bringing an extension up and attaching it to an extension of the dimension. So here we can see not only do we have to cover the actual physical size here and the depth, but it needs to be perpendicular within so much to datum A to establish or qualify this feature as datum B. So those are the four common ways you'll come across feature control frames. And in the actual course, we get into exercises as well. Like I said, unfortunately, I'm doing a lot of talking and presenting here, but in the full-blown course, there is a good combination of examples, exercises, as well as me speaking. So the next thing that I want to talk to you about is characteristic symbols. I've kind of indicated a few already, but let's talk a little bit about it. The first thing that I want to point out to you is a change in the 2018 standard. The previous standard to this was the 2009 standard. In the 2009 standard, it had concentricity and symmetry as characteristic symbols. In the 2018 standard, they've now removed concentricity and symmetry from the standard because they feel that they're redundant, that it can be covered with a positional callout by itself. So just one of the changes that we point out in the new standard as well. So when we take a look at the different characteristic symbols here, you can see how we've got the characteristic symbols and it gives you the actual name of the characteristic. And then it shows the symbol that is placed in the feature control frame in order to illustrate that characteristic. Again, we want to try and keep the problem with large wordy notes on drawings is they can often be misinterpreted. So we try to communicate through these characteristic symbols, feature control frames, and datums to help cut down on the writing with these universal standard. So here you can see the individual characteristic symbols. If I come down to the 2009 standard, they gave it in a very nice chart because not only did they show the characteristic symbols, but they also talked about the different types of tolerances. Remember that in geometric dimensioning and tolerancing, there are 5 types of tolerances. There are form tolerances, profile tolerances, orientation tolerances, locational tolerances, and runout tolerances. So inside the form tolerances, that's where you have the breakdown of the characteristics that apply to the form tolerances: straightness, flatness, circularity, and cylindricity. In the profile tolerances, we have profile of a line and profile of a surface. With orientation tolerances, we have angularity, perpendicularity, and parallelism. And with locational tolerances, we have position, concentricity, and symmetry. And lastly, with our runout tolerances, we have circular runout and total runout. So if we talk a little bit about these, when it comes to our form tolerances, our first grouping of tolerances, as I mentioned, straightness, flatness, circularity, or often you'll hear it referred to as roundness. And lastly, cylindricity. The form tolerances control the geometric shape of the part feature. They specify how much the part surface can vary from perfect geometric shape, and they're not referenced to a datum. And that's what makes the form tolerances stand out from all the rest, is they're not referenced to a datum. They're talking about the geometric shape of the actual part feature. When we talk about straightness, typically straightness is applied to a shaft. So when we have a physical shaft, not only do we have to control the actual diameter of it, but if it has a straightness callout, it's now giving us a secondary control saying that it must be straight within a certain amount. And that certain amount is specified in the feature control frame. So it's just telling us how non-straight or bent it can be and still be an acceptable part. Flatness, on the other hand, is commonly applied to a surface. I've got a surface that's mounting down onto another surface. I want to ensure that that surface is flat within a certain amount, and flatness acts in both directions over the entire surface. Circularity, often referred to as roundness, is the surface condition. So again, if we had a shaft, we'd be talking about the actual surface condition of the shaft, or the ovality of the surface at any given cross section. So circularity acts at any individual cross section along the length of the actual shaft, and it's the surface condition or the roundness of that at that particular cross section cannot be more than what's in the feature control frame. So it's not talking about the straightness, how much bend there is to the shaft. It's just talking about the surface at any given cross section. Cylindricity, on the other hand, is a surface condition as well, but it's a surface condition acting over the entire surface. So it actually gives you a combination of circularity and straightness all in that one cylindricity callout. So those are the form tolerances. And again, in the course itself, we go into much more detail. The next grouping are the profile tolerances. Remember, there was profile of a line and profile of a surface. Profile tolerance specify a unified boundary along the true profile within which the elements of the surface or line must lie. It's typically referenced to a datum or datums. So profile of a line is 2D, two-dimensional. Profile of a surface is three-dimensional. So profile of a line is typically applied to parts having varying cross sections. We have something that tapers up to a knife edge and we want to control the actual knife edge. That would be profile of a line. Profile of a surface is 3D. Not only does it act over the length of the feature, but also over the thickness. So again, our dimensions that go back to our datums tend to be our basic dimensions, giving us our theoretical perfect location of our actual surface. And then in the feature control frame, it gives you a band that the actual surface can fall within. Orientation tolerances consist of angularity, perpendicularity, and parallelism. They control the relationship of part features to one another, and again, they're referenced to a datum. So angularity, with our orientation tolerances, we're not so concerned about the location, but we're more concerned of the actual orientation. So we want to tighten up the orientation. So with angularity, it's typically applied to any angle other than 90 degrees or 180. Because if you get to a 90-degree condition, you're talking about perpendicularity. 180-degree condition, you're talking about parallelism. So angularity is typically applied to a surface or an axis that is not at 90 degrees or 180 degrees to our datum, and we want to control the orientation back to that datum. Perpendicularity is a 90-degree condition, again, can be applied to a surface or a feature of size. So in the case of a surface, you're talking about the 90-degree condition of the surface. Applied to a hole, for example, drilled through a part, you're talking about the 90-degree condition of its axis in relationship to the datum. And parallelism is the 180 degrees. We want it to be parallel to our datum in order to control that orientation. So they control the relationship of the part features to another, to a datum, and their reference to a physical datum. Locational tolerances, we have position, and up until the 2018 standard, we had concentricity and symmetry as well. They control the location of features to one another in respect to a datum or datums. They talk about how much the feature could vary from perfect location, and the reference to a physical datum or datums. So again, when it comes to position, the characteristic symbol is shown right here. We use basic dimensions to give us our theoretical perfect location. And then in the feature control frame, we see how much we can vary from that perfect location. So it's a locational tolerance. Concentricity is an axis-to-axis control. You have a step shaft or a coaxial shaft, and you're comparing the axis of the feature back to the axis established by the datum. And symmetry, I've got a notch that's machined in the middle of the part, and I want to make sure it's right in the middle. That is where symmetry would be applied. In the 2018 standard, we could now substitute position in for both concentricity and symmetry, making them redundant. Lastly, our runout tolerances. We have circular runout and total runout. Runout tolerances are a surface to axis control. You've got a step shaft. You're talking about the surface of your feature compared back to the axis established by your data. Circular runout is surface to axis, but it acts at any individual cross section. So at any given cross section, it talks about the surface condition, giving us a combination of roundness and off-center condition. Total runout, on the other hand, is a surface to axis control. However, it acts over the entire length of the feature. So it gives you a roundness, off-center condition, and size distortion. So they control the functional relationship of one or more features of a part to a datum axis, and again, a reference to a datum. So in the actual main course, we go through the characteristics in great detail, making sure that you have a clear understanding of those characteristic symbols. And we also get into comparing them as where you might use one versus another or come across one versus another. We also get into the modifiers. It's very important to understand modifiers in GD&T. The modifiers, maximum material condition, least material condition, and regardless of feature size, are discussed in detail. Maximum material condition, its symbol is an M in a circle when placed in a feature control frame. And maximum material condition on its own is the condition that gives you the most amount of material or most amount of weight. So in the case of a shaft, remember that every single feature on a drawing has a dimension, whether it be a specific tolerance or a general tolerance from the title block. So when we are talking about maximum material condition of a shaft, we're talking about the largest allowable physical feature size based on the tolerance applied to the feature. In the case of a hole, in order to have the most amount of material, the smaller the hole that's produced in your part, the more physical material you have. Therefore, maximum material condition is the smallest allowable hole. What maximum material condition does for us is it goes ahead and it adds a bonus or additional tolerance as the part deviates from maximum material condition. So what the feature control frame is saying is that we've got a positional requirement, diametrical tolerance zone of 0.002 at maximum material condition to datum references, primary datum A, secondary datum B, and tertiary datum C. So at maximum material conditions, smallest hole, we have a diametrical tolerance zone of 2 thou that the actual center has to fall within from the theoretical perfect location outlined by the basic dimensions. So our smallest hole is 495. We're allowed 2 thou, but as the hole gets larger within its allowable feature size, we get allowable tolerance added to our feature control frame. So the larger the hole becomes, the further it can shift out of position and still functionally fit in our assembly. So we go into a lot of detail on maximum material condition and understanding. We talk about terms like virtual condition, and we look at inner and outer boundaries. We'll also take a look at different applications where MMC is applied in order to, again, get a good understanding of it. We also get into composite feature control frames. Composite feature control frames, we'll talk about what a composite feature control frame, like the example you're seeing here where it's got one characteristic symbol and then it has multiple frames. We'll go in and explain pattern locating tolerance zone framework, the top one, feature relating tolerance zone framework. and we'll talk about what that actually means. And we'll explain that in detail as well. So just keep in mind that you can come across composite feature control frames in GD&T, and it's important to understand the relationship between the pattern locating and the feature relating. The actual course themselves, as I mentioned, there is 2 courses. There's a fundamentals course, which is 12 hours broken down into 3 4-hour sessions. With the fundamentals course, we talk about the benefits of geometric dimensioning and tolerancing. We get into the characteristic symbols. We get into feature control frames. We get into the modifiers. We also take a look at one method of inspecting for the characteristic symbols, and we'll do a bit of a comparison of the characteristic symbols. In our lesson 6 in there, we get into feature control frames. We take a look at partial datums, datum target points. We talk about datum modifiers. We look at kind of the breakdown of GD&T and how many datums are necessary. In lesson 7, we do a comparison between diametrical tolerance zones and coordinate tolerances. And in lesson 8, we get into composite feature control frames. In the advanced course, again, it's 12 hours. The prerequisite is the fundamentals course, but we get into going through a general review of GD&T principles, reinforcing the fundamentals course. We review the characteristic symbols. We get into a further explanation of profile tolerances, looking at all round, between points, unequally disposed, etc. We do a comparison of different characteristics, and we also get into the modifiers and go further into the modifiers. We look at composite feature control frames, and we look at segmented feature control frames and different variations you can come across with segmented feature control frames. We also get into some exercises and design applications, thinking about how GD&T is actually applied. And then we get into tolerance stacks and tolerance buildup calculations. So we take a look at things like profile tolerance stacks, boundary detail stacks. We talk about fixed fastener and floating fastener calculations. So again, we get into a lot more depth on GD&T. But again, it's a gradual building so that at the end of the 2 12-hour courses, you come away with a much better understanding of geometric dimensioning and tolerancing. Okay. I've just hit you with 40 minutes of nonstop information, and I apologize for that, but I'm trying to cram 12 hours of course into kind of a half an hour makes it a little more tricky. So what I'm going to do now, I'm just going to go ahead and turn on my video for a moment. And I just want to go ahead and just turn to the chat for a second. And let me just see here under the chat. Okay. If there is any specific questions here. Oh, wait, sorry, chat. Okay. Okay, so I'll open it up to questions. We've got about 5 more minutes, so I'll open up to questions. I believe this PowerPoint is this presentation is being recorded. So if you want to reach out to Paige from Javelin, just to see how she plans to distribute this. And other than that, I'm open to questions for the next 5 minutes. If you just want to raise your hand or unmute and ask a question. Okay, David, I believe you've raised your hand.
Yeah, what you've shown in your figures so far has all been with standard or classic sort of paper drawings, but in SolidWorks we have the MBD?
Model-based definition? Yes, we do.
Something I've looked at, but I've never sort of stepped into.
Okay.
Are you going to be dealing with both?
We do have a course. We do have a course on model-based definition. Our geometric dimensioning and tolerancing is understanding the concepts of geometric dimensioning and tolerancing and getting a good understanding of it.
Yeah.
When it comes to model-based definition, what it does is it allows you to apply the actual produce the drawing in the form of the model itself. So assign datums, assign feature control frames right to the physical model. So when you send that math data over to somebody, that information transfers with it. So it's taking all the knowledge that you learned in the GD&T courses and now being able to apply it through SolidWorks through model-based definition.
So the courses that you're talking about, are you going to be swapping backwards and forwards between the two, or just deal with paper drawing?
It's just the pure GD&T, just
Okay.
understanding the geometric dimensioning and tolerancing. And with model-based definition, you can produce PDFs to kind of as a supplement to drawings.
Yeah.
But unless you understand the concepts of GD&T,
that's fair enough. But it's
no.
I was just
Excellent question.
which form you're going to sort of communicate.
Yeah, I'm going to do it more in the form of standard drawings, so standard drawing packages.
So if you don't have a background or hadn't really thought about model-based definitions, and it could be a little confusing.
Exactly. So that's why we focus just on the concepts of GD&T, and we base it based on traditional drawing packages. Excellent.
Okay.
James, you have your hand up as well.
Yeah, it's difficult for me to maybe formulate this question, but it has to do with bonus tolerancing.
Yes.
And in a practical industrial application, you say, okay, if the hole is larger, then we can allow more tolerancing. But I'm trying to get my head around the interplay between the two. How is it inspected, or how does one come say, oh, now I know I can allow this bonus tolerancing?
So there's two things you have to step back with. Number one, maximum material condition can only be applied to a feature of size. It cannot be applied to a surface. So it's got to be a feature of size. Number two, we tend to apply maximum material condition when your design intent is that it's always a clearance application. So for example, a mounting pattern, a mounting hole pattern, where your design intent is there's always going to be clearance. You want to put a bolt through there and thread it into the mating part. So what it does is it says in that application, we have something called an inner boundary on the hole, a virtual condition. So as the hole gets larger, it makes more sense that we can let it float further out of position. But as long as the surface doesn't cross the actual virtual condition or inner boundary, we know that our parts will always go together. And we actually take a look at a couple of design activities where, we say, okay, well, what would be the size of the actual feature based on this? So just keep in mind that we only apply maximum material condition where your design intent is to apply a clearance application. Least material condition tends to be applied where you've got thin-walled or thin-walled applications where you're concerned with breaking out or compromising the wall thickness. And regardless of feature size, tends to be applied to everything else. So we go in and we do a bit of an explanation on that in the course as well. So that's an excellent question. But that bonus tolerance, we set it up as a math, actual minus virtual or virtual minus actual, and you can calculate what your allowable tolerance is based on the actual size and your calculated virtual condition.
So then practically after this is done, the hole is drilled, say, somebody then has to check to say, hey, where is the hole? What is the hole size? And then look at that virtual condition and see if it works.
Well, that's it. There's always two checks. Number one, the physical feature size. In other words, did it meet the actual diameter? Is the hole too big, too small? And secondly, is it in the right position? Because it's no use to me if it's a half an inch out of where it should be. So it's always a double check. Yep.
Thank you.
You're welcome. I've got, okay. We are coming right up to the actual 45 minutes. As I mentioned, this is kind of like a whirlwind introduction to GD&T, just to get you thinking about geometric dimensioning and tolerancing and thinking about, why it's so important. Remember that drafting is a form of communication. We want to make sure that we communicate effectively our design intent so that anyone, no matter where they are in the world or whether they know this part or not, doesn't have to make assumptions. They can go ahead and confidently understand what's required, whether they're producing the part or they're inspecting the part. Okay. So if there's no further questions, I think what we'll do is we will call it there. I want to thank you on behalf of Javelin Technologies for joining our very short webinar. Like I said, I just wanted to give you a taste of geometric dimensioning and tolerancing and how Javelin approaches it.
Thanks very much, Shawn.
Yeah, you're very welcome.